So the first talk is going to be by Marcin, and Marcin is a developer at Tantus Data in Warsaw, and he has been consulting in well, Apple, Spotify, and Telia in the past, and his talk is going to be about Apache Spark. So give it up for Marcin.
Hello. Yes. Would you like to learn what Spark is good at? How does it work under the hood? What kind of pitfalls you can face? By the end of this talk, you'll have understanding of how it works under the hood, how to fix common problems, but also you will get an overview of common use cases, so you will know what you can use it for and whether you would like to start working with Spark or not. My name is Marcin. I work at Tantus Data. At Tantus Data, we do everything related to data, basically. So from cluster installations through data application development, training, supporting of teams of data engineers and data scientists. And myself, I've been doing all of this, but on a daily basis, I act as an architect and developer. First, I'll introduce to what Spark is, and then we will have an overview of use cases. Some of them will be on a high level, some of them will be a little bit more detailed, so you get the understanding. And then we'll have a deep dive into how it works under the hood. So I'll show you a few problematic cases and how understanding of how Spark works will help to solve them. And at the end, I would like to show a little bit of a big picture. So big picture from the technology point of view, but also from the point of view of organization and processes. So I'll share my lessons learned. I'll share my conclusions from working in data projects in the past. So let's get started. Spark is a general engine for distributed data processing. So you can express your business logic in one of these languages, and it will take care of distributing the load. It will take care of spreading the load into multiple machines, so you can process your data faster, you can process larger data sets. It has a streaming API. It has a machine learning library, but for today, we're just going to focus on the core of Spark. And let's get started with some use cases I've worked on. And let's simplify it a bit. So mobile app company, we have a mobile app which connects to backend and then writes the data to a database, let's say SQL database. And what you would like to do is you would like to improve your app. You would like to improve your app by knowing how the customers behave. So you decided to store the events. What kind of events? That the user clicks a button, scroll through the screen, maybe look at a certain view in your app, and then you can connect your analysts to the database, and then they can have a look if the user, why the user have not become premium, because he went to the go to premium page by mistake and just immediately clicked the button, or maybe he was trying to, but the flow was too complex for him, or maybe the application has just crashed. And so far, so good. Your application grows, you have more analysts, they're trying to run more complex queries, maybe some machine learning. But at some point you are so successful that you have to solve some technical problems. So the number of events you've collected is huge. You are overloaded with number of requests coming to the database, and your analysts simply cannot do much with it anymore because they cannot run any query. It just runs forever or just crash. Unfortunately, it is quite well-known problem, and a solution I would like to propose is that instead of storing the events to a database, you can store it to HDFS. So if you are not familiar with it, it's a distributed file system like Linux one, but HDFS takes care of splitting large files and saving it into multiple machines. So you get scalability, replication, stuff like that for free. And then what you could do, you could expose your analyst to the Spark API. So Spark will take care of distributing the business logic they've expressed, reading the data from HDFS and returning the result or writing the result back to HDFS. And this is just to give you what Spark API looks like, just to give you an idea. And I want to emphasize on this group by, max, average, join, select. So you're familiar with SQL, so you can get the idea what this piece of code does. And the point is, it's quite simple to express the business logic if you know SQL. You also get an API which is a little bit lower level, like if you prefer to do functional programming. But the point is, it is quite simple to express the business logic and do all kind of general use cases any company has. So doing ETL, so reading data from multiple places, doing some cleanup and transformations, and writing it to some common place, or calculating KPIs, so you understand how the company is doing with acquisition, how it's doing with revenue, and tons of other use cases, A/B tests, running them and then analyzing the results. Anonymization, GDPR is coming, so it's likely that you have to do some anonymization on your data, calculating fraud, churn, running machine learning on top of that. But enough of general use cases. Let's have a look at something a little bit more complex and more concrete. Examples from telcos I was working on. And let's get started with network improvement. So telco network is a set of base stations, and customer travels around, they get reconnected, and they get various experience. Depends on the characteristic of the base station, depends on how crowded it is. And what you would like to do, you would like to improve your network, so you would like to invest some money into upgrade of the base stations, but you would like to make it smart. Your budget is limited, and what you would like to achieve by the end of the day to provide better network for as many customers as possible, so they are happier, they are more likely to stay with you. And if you think how to do that, first of all, you would have to analyze the historical probes you have from the network. So what was the customer's throughput, what was the customer's latency, and you would have to come up with a score for the network quality for each customer. Then, based on the score, you would have to come up with a churn model, so you understand how the network quality affects customer churn. Then you can simulate the actual network upgrade. So you know the characteristic of the new base station, so you can calculate what would be the network improvement for each of your customers. You have the new score, and then if you mix those two, if you mix the new simulated score with the churn prediction model, you get an idea how a network upgrade affects the probability of your customer to leave you, so the actual business value. And just 4 points, but you can imagine this is extremely hard problem in terms of the calculations you have to do, in terms of how many iterations and how smart you have the model should be. And I would say start with something simple, with linear model, and play around with it. But these kind of problems are definitely worth doing if you think about the money you invest into the network. You want those investments to be smart, and also the value you can get out of it. In companies like telcos, like large companies, any percentage change in the churn stats is a huge win. Very quickly, one more example, so social network analysis. So a lot of companies do that because social networks are highly predictive, and in telco you can do that by simply connecting your customers based on the call they make, based on the text messages that they send, and narrow it down to close friends and family groups. And then if you mix that data with historical purchases they've made, you can try to find the people you would like to target. You can try to find people who would be influencers, which means giving them an offer, giving them a good offer with brand new phone and new contract might just spread out. But this kind of problems has been there for a very long time. People have been doing that. So why do I propose to use Spark for this? The traditional way of doing this is that you get the data, you get it to some R server, or maybe the analysts take it locally, and they play around with the data, but usually the data volume is too large to just take it to one machine, so you have to either play around with some aggregates or just some samples. And then you might end up with this very well-known blind man and elephant problem. So when the blind man is touching part of an elephant, they get completely different ideas about what an elephant is. And exactly the same could happen to your data. But if you are working with a system like Spark instead, you define your business logic, but the actual processing is somehow closer to the data. So you just send the calculation, the analysis to the data, and you can work on the whole data set. So you can analyze all the data, you can do the analysis faster, so you can have faster feedback loop, you can iterate faster. Also, you don't have any extra data copies in this case, which might be quite important when we think about the upcoming GDPR. And problems which I've described, like analyzing graphs of social interactions and stuff like that, they are mostly implemented somewhere, which on Spark, which doesn't mean you can just take it out of the box. You would have to change some parameters and apply it to your problem, but it doesn't mean you have to start it from scratch. Last example of Spark use case I was working on would be analyzing geospatial data. So imagine that you would like to build a map, either general map service like Google Maps, or you are building self-driving cars and you need a map you can trust, a map which is crafted to your use case. And if you build such a map, you probably have to rely on really many data sources. So maybe you have the car which takes a picture and you blend it with artificial intelligence. You most likely have tons of editors who are looking at satellite data and customer reports and bug reports, and they draw a map and fix the bugs on the existing one. Maybe in some countries you don't want to invest yet, so you buy some data from vendors, and maybe you would like to look at open source geospatial data repositories as well, and blend that data together in order to get a new version of your map, new, better version of your map. And that means you have to get a lot of data, you have to do it quite often, you want to iterate fast. And just to give you an idea of what kind of operations you would have to do, you would have to get data from, like the road data from multiple sources and make sure there is no hole in the data. You would like to get information about like newly opened coffee house, or maybe you would like to update the pickup point for a given address because customers are complaining about that. And the whole point is data from many vendors, a lot of operations. Some of the operations are extremely expensive in terms of CPU time, and Spark gives you an easy way to distribute that data and get the many CPUs you need. So if you look at the map, in order to distribute processing of the data for a map, you just need to come up with a way to split the data into sectors. This is, of course, a little bit too simplified. Probably you want to control it better. But the point is each sector will be processed in different JVM in different machines. You get many CPUs. You process that data faster. You iterate faster. So a quick summary of the use cases. You want to use Spark if you are processing large data sets, or if your computation is extremely expensive in terms of CPU, then Spark gives you a reasonably easy way to distribute it. It gives you SQL-like interface, so analyst-friendly, but also if you have more complex problems or you prefer functional programming, it gives you such an API as well. And now I would like to do a deep dive with you. So deep dive into how Spark executes the program, how the partitioning of the data works, how the caching works. And why do I want to do it? I want you to have a bit better disaster recovery plan than this. And why am I talking about disaster recovery plans? Because from what I saw when working with clients, it is easy to implement a Spark program to express the business knowledge. Even if you test it like locally, it works. But then you go to a cluster, it fails, and you don't really know why. It's not obvious because Spark hides a lot of complexities from you. But if you are handling large data sets, it's likely that you will end up in some edge cases. So let's get started. First of all, you need to understand that when you work with Spark, you work with either RDD or DataFrame, and it looks like you're working with local collection, but the collection is not local at all. It is split into multiple partitions, which are likely on different machines. And then Spark can do two types of transformations. First of all, the simple ones, which work on one and only one partition. Spark does not have to exchange data between partitions. So if you do a 2 uppercase for each record in your data set, if you do 2 uppercase for each record in your data set, you don't really need to exchange the data between partitions. You just do it in place. And Spark uses that knowledge, and it pipelines this kind of operations. So if you do 2 uppercase and then reverse on a string and so on, these kind of operations can be pipelined, and they form a task. So they are done in place. Task is the simplest, the most granular execution unit in Spark. And one partition means one task. But, of course, you would like to express something more complex. You would like to do join of your data or group by key and stuff like that. So in order to do that, Spark has to pull the data from multiple places into one. So user ID 1 goes to one partition, user ID 2 goes to another one, and user ID 3 goes somewhere else. And it doesn't necessarily have to look like that. This is something you don't explicitly control because it's just a hashing algorithm, so we might end up with something like this. Although you can control how many partitions there will be in the output. So it might be like this, or like this, more or less. So from 10,000 feet, Spark application looks like the following. As an input, you have a partitioned data set, and then Spark tries to apply as many simple operations as possible. So they work on one and only one partition. But at some point, you do, let's say, join, and Spark has to shuffle the data over the network. And then it tries to do simple operations again, and then you shuffle the data again because maybe you're doing group by key. So the shuffle is something which is expensive, a lot of I/O is involved, and also a lot of things which can go wrong, and we will be looking at it in details. And let's get started with the simplest scenario ever. Let's say you are reading some data set from HDFS, and this data set has a timestamp column. And out of that, you would like to calculate information about a year, a month, and a day when given event happened. And Spark will pipeline of all these operations because they are simple. Nothing really can go wrong. It just reads a record and calculates a year, month, a day out of it. And then maybe you would like to store the result to HDFS. And this will be one task. So Spark will read one block from HDFS, pipeline all the operations you requested it to, and it will write a new file to HDFS. How many of such tasks you will have? Let's assume you have 1 terabyte of data in 1,000 files, and each file is 8 blocks, means 8,000 blocks, 8,000 tasks. Each task will do exactly the same. The only difference is it will be reading different portion of your data, different blocks from HDFS. And each task gets run on an executor. Executor is a JVM somewhere in your cluster. When you start your Spark job, you control how many executors you want to give it, how many CPU cores you would like to give it, and how much memory. So let's look at something more complex. Imagine you would like to join events dataset, quite large, with some small dataset of users. And let's imagine our events are uniformly distributed between users. So there are roughly the same number of events with the same user ID. So what will happen is Spark, again, will read one block from HDFS, and then it will organize the events data based on user ID. It will write some portion of the user's ID to bucket 1, to local disk, some portion of the users to the bucket 2. And the rule is that if 2 events are for the same user ID, they go to the same bucket. All the other tasks for events and for users will do exactly the same. And then Spark will create another set of tasks. Those tasks will be performing the actual join. So they will be pulling the data over the network, the data belonging to the same user ID. So this task is performing part of the join for bucket 1, then for bucket 2, and so on. So how many of these tasks will have? The default is controlled. This is controlled by a single parameter, and the default is 200. And what does that mean for us? 10 terabytes of events multiplied by 200 tasks is 50 gigs. So each of these tasks performing part of the join will have to handle 50 gigabytes of data. It's a JVM. You probably don't want your JVM to be this large for just performing a join. And it doesn't necessarily mean it will fail, because Spark can spill the data to disk, but that still degrades your performance. But also, it's likely that you'll see something like this: garbage collection problem, out of memory problems, or any problem which at first glance it won't really look related to what you're doing, but you have to deal with them. So first of all, you have to understand the problem. You have to understand where it's coming from, what the size of your data is, and how many partitions you should have instead, how many tasks you should have instead. But once you understand that, solution for this problem is quite simple. Just increase the level of parallelism. So this is how you do that, depend on which API you are using. So let's have a look at something trickier. A skewed join. So we have 10 terabytes of events, but then one user ID has many more events than the other ones. So one user ID has 1 terabyte of events, and you would like to join the data and just save it to disk. Nothing complex. So you would like to join the events with user to just add some extra information. What will happen is exactly the same, let's say, query plan. But the problem is one of these tasks will have to process 1 terabyte of data, because how Spark implements it is it pulls all the events, all the user IDs, because you are joining based on user ID. It pulls all the events with this user ID to the same machine, and this will crash for sure. So what do you do with this? First of all, you have to understand where this skew is coming from, because it is likely that you have a problem with your data. Maybe your data delivery mechanism is broken, and you end up with user events with user ID null, and you have to fix that first, because otherwise the analysis doesn't make much sense. Then maybe it's a wrong logic, so you calculate your data frame in multiple steps, and at some point you introduce a bug and you end up with null or something, some dummy value, which again doesn't make sense, so you have to fix that first. But if it's just okay, if your data looks like that and you still would like to perform the join, this is a quite simple technique. So here we have user ID 1, which is the problematic one. We have many of them, and we want to process them in multiple tasks. So what we can do is we can provide a salt column. So we are introducing some randomness to the events. I have randomly generated the users from 1 to the salt from 1 to 3, and this is just random value. Then user IDs we would have to duplicate. So user IDs, we create a user ID with each possible salt. So we have 3 times more users. And then, if we perform the join, we perform the join not only based on user ID, but also based on salt. So one task will process this users. This task will process just one, and this task will process again part of your data. So a quick recap of Skewed Join. Know your data, understand where the salt is coming from, but if it is something you still want to do, you still want to do this skewed join, add a salt. This is a very simple technique. You just have to be careful about the logic. You just have to make sure that adding the salt does not change your logic, but this is a good, good starting point. And last technical part for a deep dive I would like you to understand is caching. So first of all, why do we need to cache the data in Spark? The reason is transformations are lazily evaluated, so they are evaluated once they need it, once you want to materialize the data. But that also means the partial result never gets stored to disk. So if you want to reuse some of your logic, and if you want to, let's say here, RDD1 is calculated out of the blue transformations, and then you would like to do some extra transformations on top of that and write the result to disk, and then you would like to do something similar once again, the blue transformations will happen twice. And to give you an overview what that means for the case of PageRank algorithm, the core of PageRank is that you have to do join of two dataset links and ranking multiple times. You do it in iterations. So first you do a join and you calculate new ranks. Then you do the join with the new ranks again, and so on. That means you have to read that data from disk multiple times, unless you use caching. If you use caching, the links will get stored to memory once they get read from disk for the first time, and then you will reuse the data from memory. So in order to do the caching well, first of all, you need to spot which data to cache, and the candidates for caching is any place where you reuse the objects you are working with, the data frames or RDDs. Then, in order to do it smart, you have to understand the size of your data and how expensive they are in the calculation. And you have to know that because you cannot really pin an RDD to memory. You cannot set priorities, just LRU algorithm. So caching second data set might mean you lose the first one. So you have to be smart about it. You have to know what's important to cache, what is expensive to calculate, so you can reuse that. There are tons of other gotchas we don't really have time for, but I would be happy to discuss them later on. And really, the whole point is that you need to understand the data and you need to understand how it works under the hood in order to write performant Spark programs. And now I would like to do a little bit of bigger picture. So this is what I show you in the beginning for the mobile app company, but it's likely that you will want to read the data from multiple sources and write the data from to multiple locations. And maybe you'd like to use Druid or maybe Elasticsearch if you want to do dashboards. And if you Google for that, you can very easily find a code which connects to all of these systems, and it's not a problem at all to write it. But I would say be careful about what you introduce to your ecosystem. Make sure you not overcomplicate things. Make sure the things which you are introducing to your system make sense. And also make sure you understand the basic characteristics of those things. Because if you are connecting to Postgres, well, you can very easily distribute Spark processing, but if your main data source is Postgres, it just won't work. So understand the systems you are working with. And this is the big data landscape. You need like lifetime to understand all of them, so be smart. And you came here, which means you are interested in data. These are a bunch of challenges which probably you will have ahead, and they are not necessarily Spark related, but you will have to come up with 5 file formats you would like to use, how to deal with data evolution so you don't get stuck with some schema, how to build pipelines, how to monitor them, and how to monitor the data itself, how to organize machine learning models so you keep track of them and you understand what is built of what and how to use the output and which one is the good output right now, and so on. So because of that, I would say you should come up with some common tools and knowledge you are sharing, and you should do that from day one, because like if you, just to give you an example, like analysts is not very much interested in JVM problems and in garbage collection, and he should not be. But on the other hand, you should expose them to most common problems they might face and how to write performance queries, so they can do it on their own and they are not blocked by just the fact there is some simple problem and which they don't understand because they just rely on the SQL interface. If you know a little bit more about, if all the people who are working with the systems in your infrastructure are familiar with most common problems, it really helps to all of you. And last picture I would like to show you is the hierarchy of needs in the data science. So deep learning and machine learning, this is something everyone wants to do. And sure, you can go back, you can just manually pull some data and do some dirty POC real quick. But if you are serious about that, if you want to make sure you can benefit from that on daily basis and you can improve your product continuously, you need to make sure you can rely on the data delivery mechanism is reliable, you have monitorings on top of that, and so on. And this is, again, something to start with from day one. So the conclusions, the top 3 conclusions are Spark can help you with distributing the load, with crunching a lot of data. But you should know how it works. That really helps if you want to build performant programs. And the big picture, the whole infrastructure, think about it from day one. Think about the direction you are going to. And yeah. I will be happy to answer your questions now. And also, if you follow me on Twitter, I plan to do a write-up and describe a little bit more details about what I've been talking about. And also I'll write a summary of the questions I will get either now or maybe during the, maybe later, yeah.
1 second, please, 1 second. Here we go. Because otherwise we cannot record it.
Thank you very much. I have several things, but really short. You spoke 2 times about the functional paradigms in Sparks. Mm-hmm. I would like to know if it's best practice to use a Scala or also Rix Java is possible as a way to interact with the functional paradigm in Spark. The second thing is related to the problems with the cache, with the garbage collector. Actually, for the garbage collection, I would like to ask you if it's like the normal Java, that you are completely, basically, independent by the framework, or you can allocate in Spark the heap for each executor so that you can kind of having an architectural strategy for the garbage collection. And most important, testing. We didn't speak about testing. To prevent problem like in the skewed join, for instance, where you have all these problems, what you do as a testing strategy, you do test-driven development, you do some mocks, you do some Monte Carlo simulation, you do some integration testing, because I think it could be central to this. Thank you.
Okay. So let's start with...
These were 3 questions, right?
Yes.
Yeah, okay. So the first one. Yeah.
The last one, because that one I remember.
Like it.
So testing, definitely test your code, and problems like Skewed Join is really hard to test. So it's more coming with you understanding the characteristics, the data stats you're running, and the only thing you can really test locally is the fact that the way you solve the skewed join problem does not really break your logic. But testing, generally speaking, testing, doing TDD or all kind of approach you would like to do, it's definitely something you should do, because it makes you iterate faster. If you have your logic implemented and then you go to a cluster and something breaks, it is just much slower to figure out what was that, and it is much slower to iterate. So, and it is even slower than with with general, like if you build web app, you get the feedback loop much faster. But with Spark, it might be that you want to crunch a data set, you leave it for like half a day, and then you get a bad result, and then what do you do? Then you have to figure out where it is. So test as much as you can locally, and it is quite easy to test the business logic, at least locally. Spark can be run in local mode, and no problem with that. The other two help me.
Oh, I would say, 1 second. I would maybe give the choice also to other people, and maybe you can discuss during the break. Good. Is there someone else who has a question? If nobody has a question,
we can discuss it later.
We have some reserve questions, so it will be good. No one? Yeah, you have a question?
Yeah, sure. Hey, so a few points that you touched upon said that you really need to understand your data. That's a valuable thing in doing Spark development. Do you have some tips on how to actually get that knowledge about your data? I mean, you can figure stuff out when stuff is running. Mm-hmm. You can see stuff in your Spark UI, but that may be too late. Yes. Do you have some pointers there?
So Spark UI, well, it tells you something about like what went wrong, but if something went wrong, it's already quite late. But it is quite often that Spark UI gives you an overview of that something went wrong, but it doesn't really tell you anything about, let's say, your key distribution. So I would say when you write your program, first of all, you can go to, let's say, Spark Shell and do some interactive analysis of the data you are running. And if you expect that, if you are not sure about the data which will come in the future, it might make sense to use accumulators. So Spark can accumulate some stats about the data and output it somewhere. So at least when you run the program and something went wrong, it can give you some idea of what was that. It makes your code a little bit clumsy. And if you do any extra stats, it's something, well, it also affects the performance. So we need to find a balance, and well, it depends on the situation. But if you are touching a data set for the first time, it definitely helps if you go to some interactive programming with the data, so you get some stats, you see what it looks like.
Other questions at the moment? Yes.
So you talked about use cases for Spark and problems with partitioning, but sometimes there's a more fundamental problem. So everything you do in Spark is still like map reduce, right?
Right.
And so I'd like to know, have you come across examples, maybe in your work with Spark, where you just had to admit like, okay, this cannot be done in MapReduce, or do you have like suggestions for workflows which might be difficult at all to code in MapReduce style?
So I have not come with an example as such, but an example of thing which some people are struggling a lot, is that you cannot really control what is going on with each executor and inside each task. So, for instance, some people are complaining that they cannot instantiate an object based on per executor. You can do that per task, but it's much harder to do per executor. So this kind of stuff. So it's useful. The examples they were talking about, I've heard, is about logging systems, which needs to be instantiated just once per your JVM. But I would say this is very, very minor, and in most use cases, it was just fine to work with the MapReduce model. But if you have such examples, I would really like to hear them.
Okay. If there's no more questions, then I would like to go for a break, half-an-hour break. I see no hands, so I say, I see you back in half an hour. Thank you, and thank you, Marcin.
Feel free to reach out to me.
Yes.
Thank you.
Especially with the migraine.